You've mastered prompt engineering, you've built those customer support chatbots, but what if your AI could do more? Like, what if it could actually think, remember things, set goals, maybe even learn and adapt on its own? Today, we're not just, dipping our toes in, we're taking a real deep dive into agentic design patterns.
Welcome. Yeah, our mission today is basically to give you a Python beginner, maybe 6 months in, but already good with prompt engineering, a kind of mental roadmap, a way through the core ideas of agentic AI. We want to show you how you can use these patterns to build, well, even better AI solutions, especially for something really critical like supporting domestic violence crisis response organization.
Right. Think about the chatbots you might have built. They react, they respond. Agentic patterns, though, they're about making them proactive. Agents that can handle complex stuff, find information, make progress towards a goal, a clear, sometimes literally life-saving objective. We're really talking about transforming those reactive systems into, well, truly intelligent partners.
Exactly. Yeah. We'll break down the key concepts, the jargon, the architecture from the Agentic Design Patterns framework. We'll focus on 4 main areas: model context protocol, memory management, goal setting and monitoring, and learning and adaptation. No fluff here, just, thoughtful questions, structured explanations. We want to make learning this smooth, intuitive, so you can get creative and efficient in supporting those domestic violence crisis response organizations with AI.
Okay, let's unpack this then. To be a real agent, an LLM needs to do more than just, spit out text. It needs to step out into the world, right? Interact with external systems, pull in real-time info. But how does it manage that without needing a custom integration for every single tool or database out there? That sounds like a nightmare.
It really does. And you're right. What's fascinating here is that for LLMs to be effective agents, they must go beyond just text generation. They absolutely need interaction with the external environment, accessing current data, using software, running tasks. The Model Context Protocol, MCP, that's what tackles this exact need. You can kind of think of it as a universal adapter.
A universal adapter. Okay, that sounds incredibly useful. So it lets, like, any LLM connect to any external system. Is that the idea?
That's pretty much the core idea, yeah. Imagine like a universal power outlet. It lets any device, doesn't matter who made it, Gemini, GPT models, Mixtral, Claude plug into any power source. MCP is an open standard. It's designed to standardize how these LLMs communicate with all sorts of external resources, databases, APIs, customer tools, you name it. Its whole purpose is to simplify how LLMs get context, how they execute actions, how they interact with all these different systems consistently, predictably. It really cuts down on those integration headaches.
I see. So it's standardizing the connection points. What does the actual architecture look like for this protocol? How does it work under the hood?
Well, MCP works on a client-server architecture. Pretty standard stuff there. You've got the MCP server. This is the part that exposes 3 key things. First, resources. Think static data like a PDF file or maybe a record from a database. Second, interactive templates. These are basically prompts that help guide how the LLM interacts with something. And third, actionable functions, which people often just call tools. These are actual functions that do stuff like sending an email or querying an API.
Okay, so the server provides the stuff the LLM can use.
Exactly. And then you have the MCP client. This could be the application hosting the LLM or maybe the AI agent itself. It's the part that consumes those elements from the server. The overall goal here is just to dramatically cut down the complexity of plugging LLMs into all these different operational environments.
That makes a lot of sense. The agent talks to the server talks to the tool. Seems cleaner. But, okay, this reliance on external systems, it raises a question for me. How do we make sure those external systems, the APIs the MCP server exposes, are actually designed well? Designed in a way that helps the agent, not holds it back.
That's a really, really crucial point. MCP is the contract, right? It defines this agentic interface, but how effective it is, that totally hinges on the design of the underlying APIs it's exposing. Developers really need to be careful. You can't just wrap old legacy APIs without thinking about it. That can be really suboptimal for an agent. For example, say you have a ticketing system API, but it only lets you pull full ticket details one by one. If you ask an agent to summarize high priority tickets, it's going to be super slow and probably inaccurate if there are lots of tickets.
Right, because it has to pull everything just to find the few it needs.
Exactly. To be truly effective, that underlying API needs improvements. It should have deterministic features, things like filtering and sorting. Those features help the non-deterministic agent, the LLM, work much more efficiently.
And what about the format of the data itself? An agent needs to actually understand the information it gets back, doesn't it?
Oh, absolutely. An API is only useful if its data format is something the agent can actually work with, and MCP itself doesn't enforce that part. So if you have an MCP server for, say, a document store, but it returns files as PDFs, well, that's mostly useless if the agent can't actually parse PDF content. A much better approach would be to first create an API that returns a text version of the document. Maybe Markdown, something the agent can actually read and process.
Okay, let's connect that to our listener's call, the domestic violence crisis agent. How does this API design issue play out there?
It's critical there. Imagine your crisis agent needs to find shelter options. If the local shelter database API only lets you fetch all the shelter details at once, your agent can't quickly answer a specific urgent need like, find shelters with open beds for families with pets right now. The underlying API needs to support direct, filtered queries, something like get shelters, family size 3, pet salad true, immediate availability true. Similarly, if your agent pulls legal documents, maybe informational pamphlets, but they're image-based PDFs, it's basically useless. It can't summarize legal aid options or explain rights clearly to a survivor if it can't read the text. It needs processable text.
This whole idea of agents using external tools, it sounds pretty familiar. Many of us, especially if we're good with prompt engineering, have probably used tool function calling with LLMs. Is MCP just, another name for the same thing? Or is there a real difference?
That's a great question. And yeah, it's a really key distinction to make. They both serve to extend what LLMs can do beyond just text, absolutely. But they differ quite a bit in their approach and their level of abstraction.
How so?
Okay, so tool function calling, that's usually a direct request. It's one-to-one. The LLM makes a call to a specific predefined tool or function. It's often proprietary, it varies between different LLM providers like OpenAI or Anthropic, and the LLM is explicitly told, okay, these are the exact tools you have available. The integrations tend to be tightly coupled with that specific application and that specific LLM.
Right. And MCP, how is that different?
Model Context Protocol, MCP on the other hand, is designed as an open standardized protocol. The big goal is interoperability between different LLMs and different tools. It's a broader framework. It defines how LLMs and these external tools discover each other and communicate. It uses that client-server architecture we talked about. Your LLM-powered applications, the clients, connect to various MCP servers, which represent the tools. And here's a crucial difference. MCP enables dynamic discovery. The client can actually ask a server, hey, what tools or resources do you offer, instead of having them all hard-coded up front. This promotes building reusable, standalone MCP servers that any compliant application can just plug into and use.
Okay. So if tool function calling is like giving an AI a specific set of custom-made wrenches and screwdrivers, MCP is more like creating a universal, standardized power outlet system. Any compliant tool from any maker can just plug in.
That's a perfect analogy, yeah. Tool function calling is great for fixed tasks with known tools. MCP is like building that universal workshop where you can dynamically bring in new tools as needed. So, the rule of thumb. For simple apps with a fixed, small number of functions, direct tool calling might be totally fine. But if you're building complex, interconnected AI systems, maybe ones that need to adapt over time, or if interoperability is really important, then a universal standard like MCP becomes pretty essential.
Okay, so bringing it back to the crisis response context.
Yeah.
How does MCP truly make a tangible difference for an agent trying to help a domestic violence crisis organization? How does it move beyond just chatting to actual, concrete, maybe even life-saving action?
This is exactly where it gets really compelling, I think. With MCP, your agent wouldn't just be able to talk about resources. It could securely access and interact with them. Imagine the impact. An agent that can dynamically query a local vetted database of safe houses, check real-time bed availability through an API, maybe even send a secure, templated email to a human support worker to initiate a handover, all through a standardized, auditable interface. That's a huge step up.
Can you give some more specific examples of how that might work?
Sure. Let's think about practical applications. Database integration. Your agent could query local datasets, maybe Google BigQuery, maybe a local SQL database holding support service info or shelter availability. It could retrieve real-time info, generate anonymized reports, maybe even update records based on natural language commands from a caseworker. No need for custom database connectors for every single source, just current relevant data instantly. External API interaction. Your agent could fetch live policy updates from government websites. Or maybe securely pull anonymized data from a partner organization's CRM, if authorized, of course. It could send templated, secure emails to specific contacts within the crisis response network. This hugely extends its reach beyond just conversation. Reasoning-based information extraction. This is interesting. Instead of just giving a link or a whole document about, say, legal rights, an agent using MCP could actually analyze the text of that document through an MCP service. It could extract the precise clause detailing specific protections for survivors. So it directly answers a complex question accurately, not just handing over a reading assignment. Custom tool development. As a developer supporting a crisis org, you could build very specific, helpful tools. Maybe a tool to anonymously check local bus routes in your shelter, or a tool to find nearby legal aid clinics based on a zip code. You expose these simple functions via an MCP server, maybe using FastMCP, which we'll touch on. Suddenly, these specialized internal functions are accessible to your AI agent. Complex workflow orchestration. Think about putting it all together. An agent could retrieve anonymized survivor details from a secure database, Tool 1, find suitable legal aid and shelter options using other MCP services, Tool 3, draft a tailored informational message based on that, then send it securely, Tool 4, all by orchestrating interactions with different standardized MCP services.
Wow. That really paints a picture of an AI moving from just conversation to complex coordination and action. It sounds like a monumental leap forward. What other sort of considerations should our listener keep in mind when they're thinking about implementing MCP?
Yeah, there are definitely a few other crucial aspects. We mentioned discoverability, right? That's a huge advantage. The MCP client dynamically queries the server. What can you do? This just-in-time discovery is really powerful for agents that need to adapt, maybe pick up new capabilities without needing a full redeployment. But of course, with external access comes significant responsibility.
Like security.
Absolutely, number one, security. Exposing tools and data, especially sensitive data like in crisis response, requires really robust security measures. Any MCP implementation must include strong authentication and authorization. You have to control which clients can access which servers and exactly what actions they're allowed to perform. That's non-negotiable. Then there's implementation. While MCP is an open standard, actually implementing it can be complex. But the good news is providers are starting to simplify this. We're seeing SDKs like from Anthropic or tools like FastMCP that abstract away a lot of the boilerplate code, making it easier to get started. Error handling is another big one. You need a comprehensive strategy. The protocol needs to clearly define how errors, maybe a tool fails or a server is down or the request was bad, get communicated back to the LLM. The LLM needs to understand why something failed so it can potentially try a different approach or escalate to a human. You also need to consider deployment. MCP servers can be run locally, maybe right alongside the agent. That's good for speed and for security with highly sensitive data. Or they can be remote, shared across an organization for scalable access. And just technically, the protocol defines the underlying transportation mechanism. JSON RPC over standard I/O for local interactions, and web-friendly protocols like streamable HTTP or server-sent events SSE for remote connections. The SDKs usually handle this part for you, though.
Okay, so let's get hands-on for a moment. How would our Python beginner, the one with about 6 months of experience, actually start interacting with this? Maybe using something like the Agent Development Kit, the ADK.
Yeah, the ADK makes this pretty accessible. It gives you structured components. Let's look at two things. Connecting to an existing MCP server, maybe one that handles file system operations, and then how you could easily create your own simple MCP server with a tool called FastMCP.
Okay, connecting first. How does that look in ADK?
All right, for the agent setup with MCP toolset, you typically have an agent.py file. Inside that, when you're defining your Elm agent, you'd add MCP toolset to its tools list. You configure it using, say, CTOI server parameters if you're connecting to a local server process running via standard input-output. The command parameter tells ADK how to start that server. It might be npx if you're using a Node.js-based community server, or maybe just Python 3 if it's a Python server you built. A key argument you'll usually need is target folder path. This must be an absolute path to a local directory that the MCP server process has permission to access. You might use os.makeDirs in your agent setup just to ensure that folder exists before the agent tries to use it. Then you give your Elm agent an instruction, something clear like, help the user manage their files, you are operating in the following directory. Target folder path. You can also optionally add a tool filter. Maybe you only want the agent to be able to list files and read them, not write or delete. So you'd filter for list directory, read file.
And how does this specific example, interacting with local files, connect back to the crisis agent goal?
Good connection. This example demonstrates how your crisis agent could securely interact with a local controlled directory. Imagine a folder containing vetted informational brochures, maybe blank consent forms, or critical internal procedural documents. Your agent, using this MCP toolset, could list the available files for a human worker, read the content of a specific brochure when asked, or maybe even, with very carefully set permissions, save a completed intake form. It becomes a powerful digital assistant for the human crisis worker, giving them quick, reliable access to necessary, approved information right from the chat interface.
Got it. So after setting up the agent code, how do you actually run it and see it work?
Right, so to connect the MCP server with ADK Web, it's usually a two-step process in your terminal. In one terminal window, you start the MCP server itself. The command would depend on the server, maybe something like npx at Model Context Protocol Server File System Target Folder Path. Then, in a separate terminal window, you navigate to the parent directory where your agent scripts agent.py lives, and you run the command adricweb. This launches the ADK Web UI in your browser. Once it loads, you'll see a drop-down list of your available agents. You select the one you just configured, maybe called File Systems Assistant Tangent, and then you can just start chatting with it. Try prompts like, show me the contents of this folder, or can you read the sample.txt file for me? And you should see the agent use the MCP tool to perform those actions.
Okay, that covers using an existing MCP server. What if our listener needs a custom capability, something specific to the crisis organization? How easy is it to create their own MCP server in Python?
That's where FastMCP comes in, and it's designed to be quite straightforward. FastMCT is a high-level Python framework specifically built to streamline developing MCP servers. It gives you an abstraction layer, handles a lot of the underlying protocol complexities, and lets you, the developer, focus on writing the core logic of your tools. A really key advantage is its automatic schema generation. FastMCP intelligently looks at your Python function signatures, your type hints, like name.str and your doc strings, and uses that information to automatically construct the interface specifications that the AI model needs to understand how to use your tool. This saves a ton of manual configuration effort.
So less boilerplate, more focus on the actual function. How would you set up a basic server with it?
It's pretty clean. First, you'd pip install fastmcp. Then, in a Python script, let's call it fastmcpserver.py, you'd start by importing fastmcp and creating an instance, MCP server fastmcp. To define a tool, you just write a standard Python function, say greetName, drySCR, worldahmore. You add a doc string explaining what it does, greets the person by their name. Then, you register this function as an MCP tool using a decorator at mcpserver.tool right above the function definition. That's basically it for the tool definition. The doc string automatically becomes the description the LLM sees. Finally, at the bottom of your script, you'd have the standard Python entry point. If name equals main, mcpserver.run, transport HTTP, host, 1217-bit 0.0.1, port 8000. This starts the server, listening for HTTP requests on port 8000.
And how does this capability, defining custom tools easily in Python, map back to the listener's goal of supporting a crisis response organization?
Oh, this is incredibly powerful for that goal. You could define custom tools tailored exactly to the organization's workflow and security needs. Imagine a tool decorated with at mcpserver.tool called log-anonymized interaction, surviverid.str detail.str-tierbool. This function, running locally and securely, could write a structured, anonymized log entry to a local database or secure logging system whenever the agent completes a significant interaction. Crucially, the logic is contained in your trusted Python code. Or maybe send secure notification, contacted.str, message.stayur.itstr. This tool could use a pre-approved secure channel, maybe an internal API or a specific email gateway, to send an alert or summary to a designated human supervisor or support service, but only to pre-authorized contacteds defined in your secure server code. FastMCP makes defining these custom, domain-specific, and potentially very sensitive tools in Python remarkably easy, all while adhering to the open MCP standard for interoperability. You're not locked into proprietary function calling, you're building reusable, secure components.
That's fantastic. So you build your custom server with FastMCP. How does an ADK agent then use that running server?
Consuming your own FastMCP server with an ADK agent is very similar to consuming the file system server we talked about. You'd set up another ADK agent, maybe FastMCP greeter agent.pa. This time, when you configure the MCP toolset, you'd use HTTP server parameters instead of Stdao server parameters because your fast MCP server is running as an HTTP service. You'd provide the URL of your running fast MCP server, which is typically http://localhost.8000 or http://127.0.1.8000 if you use the defaults. Again, you can use tool filter greet if you only want this specific agent to use the greet tool. Even if your server exposes others, you'd give the L agent an appropriate instruction like you are a friendly assistant that can greet people by their name. Use the greet tool. Then, for testing, you run Python fastmcpserver.po in one terminal. In another, you run addqueb, select your fastmcp greeter agent, and try prompting it with something like greet John Doe. The agent should call your running fastmcp server to get the response.
This modularity really sounds like a game changer. Your main agent, maybe focused on empathetic conversation, can just seamlessly call out to these specialized, locally defined fast MCP tools like looking up a specific resource or logging in interaction without needing a major redesign itself.
Exactly. That modularity is absolutely key, especially for complex and sensitive applications like crisis response. It allows for robustness. If one tool fails, the main agent might be able to try another or handle the error gracefully. It allows for specialized development. Different teams could build different MCP tools. And it enables really creative AI solutions by composing these different capabilities together. It's a much more scalable and maintainable approach than building one monolithic agent that tries to do everything.
Okay, so MCP gives our agent the ability to interact with the world, use tools, perform actions. That's huge. But for any meaningful interaction, especially one that builds trust over time, like in crisis response, the agent needs to remember things, right? Remember what happened earlier in the conversation, maybe even remember things from previous conversations. How do we give our AI a real memory?
Absolutely. You've hit on the next critical piece. Effective memory management. It's foundational. Without it, agents are just goldfish, right? Reacting only to the immediate prompt. Just like us humans, agents really need different kinds of memory to operate efficiently, to make informed decisions, maintain that crucial conversational context, and actually improve over time. It goes way beyond basic question answering.
So what are these different kinds of memory that an agent needs?
Well, broadly, we can think about two main types. First, there's short-term memory, sometimes called contextual memory. This is very much like our human working memory. It holds the information that's currently being processed or was very recently accessed. For LLM agents, this primarily exists within what's called the context window. That's the recent chat history, the agent's own replies, the results from any tools it used, maybe even internal thoughts or reflections the agent generated. Now, modern long context models are expanding how much fits in this window, which is great, but it's still fundamentally limited and it's ephemeral. Once the conversation session ends, or if the context window gets too full and old stuff scrolls off, that information is lost. Plus, reprocessing that entire history every single turn can be inefficient and costly. So efficient management here often involves techniques like summarizing older parts of the conversation or maybe emphasizing key details to keep them top of mind within the window.
And how does that short-term memory apply specifically in a crisis chat?
Oh, it's absolutely vital for building immediate trust and rapport. When a survivor reaches out, the agent needs to remember the last few messages. It has to maintain empathy, keep the conversation coherent, and crucially avoid asking the same questions over and over again. That immediate recall makes the survivor feel heard and understood, which is paramount in establishing a safe space.
Okay, that's short-term. What's the other type?
The other type is long-term memory, or persistent memory. This acts as the agent's repository for information it needs to retain across different interactions, different tasks, or just over extended periods. Think of it like our own long-term knowledge bases. This memory is typically stored outside the agent's immediate processing environment, outside that context window. It might be in a traditional database, a knowledge graph, or very commonly these days in a vector database.
Vector database. How does that work for memory?
Yeah, it's a really powerful technique. In a vector database, information, maybe chunks of text from past conversations, documents, user profiles, is converted into numerical representations called vectors or embeddings. The neat thing is that pieces of information with similar meanings end up having mathematically similar vectors. So instead of searching for exact keywords, the agent can search for information that is semantically similar to its current need. This is often called semantic search. So when the agent needs information from the past, it doesn't just rely on its short-term context window. It formulates a query, searches this external long-term memory store, like the vector database, retrieves the most relevant pieces of information based on semantic similarity, and then integrates that retrieved context into its short-term memory to generate a more informed response.
So the agent can actually build up a history, a knowledge base that persists beyond just one chat session. How could that apply to providing continuous support for a survivor who might interact with the agent multiple times?
This is where long-term memory becomes truly transformative for ongoing support. Imagine being able to remember anonymized user preferences across sessions. For example, knowing that a particular survivor strongly prefers text communication over voice calls, or remembering key details about past issues they discussed, specific elements of a safety plan they were developing, or important disclosures they made weeks or months ago. Retrieving this relevant history when a survivor re-engages allows for vital continuity of care. It provides truly personalized support. The survivor doesn't have to repeat their entire story every time. This moves the interaction from being purely transactional to building a relationship of sustained, informed assistance, which can be incredibly valuable.
Okay, these memory concepts are clearly crucial. How does a framework like Google's Agent Developer Kit, the ADK, specifically help developers manage this complexity? Does it provide tools for both short-term and long-term memory?
Yes, it does. The ADK offers a really structured and, I think, quite robust method for managing both context and memory. It simplifies things through three core concepts: session, state, and memory, and each of these has associated services to manage them.
All right, let's break those down. What's a session in ADK terms?
A session, specifically the google.adk.sessions, session object, represents one individual chat thread or conversation instance. It basically encapsulates all the data relevant to that specific conversation. It has unique identifiers, like an ID, the app name, a user ID. It contains a chronological record of event objects. These represent things like user messages, agent replies, tool calls, state changes. And importantly, it includes a storage area for temporary conversation-specific data, which ADK calls state. The life cycle of these sessions, creating them, recording events, terminating them, handling state updates, is managed by the session service.
And you mentioned different ways to store these sessions.
Right. The session service has different implementations depending on your needs. There's an in-memory session service, which is fine for basic testing, but the data isn't persistent. If your app restarts, the sessions are gone. For most real-world applications, especially something like crisis response, where history is critical, you'd use the database session service. This provides persistent storage using a database like SQLite, for example, sqlite.myagentdata.db, or PostgreSQL. You'd need to pip install Google at Squalchemy to use this. And for really large-scale production deployments on Google Cloud, there's the Vertex site session service, which leverages the underlying Vertex AI infrastructure for scalability and management. This one requires pip install Google at Vertexa.
So using that database session service would mean that even if the agent or the whole system restarts, the critical conversation history with a survivor isn't lost.
Exactly right. Each individual chat a survivor has is a session. Using database session service ensures that the history persists. This is absolutely essential for things like auditability, being able to follow up later, and just maintaining trust in a sensitive context. You can't afford to lose that history.
Okay, that covers the session, the container for the chat. What about state? You said that's part of the session.
Yes, state, which you access via session.state, is the temporary working memory for the duration of that specific conversation. You can think of it as the agent's scratchpad for that particular chat. Under the hood, it operates like a Python dictionary. You can store serializable Python types in its strings, numbers, booleans, lists, dictionaries. It allows the agent to retain and manage details relevant only to the current interaction. Things like user preferences expressed in this chat, the progress on a specific task happening now, or maybe conditional flags that influence the agent's next actions within this session.
Can you scope this state, like make some state specific to the user across all their sessions?
Yes, that's a key feature. ADK uses key prefixes to organize state and control its scope and persistence. If a key has no prefix, the data is session-specific. It only lasts for the current chat. If a key starts with the user prefix, like user.prefers-male, that data is associated with the user id and persists across all sessions for that user. This is how you'd store long-term user preferences. An app.prefix means the data is shared among all users of the application, maybe for global settings or shared counters. And a temp prefix indicates data that's valid only for the current processing turn. It's not persistently stored even within the session. It's super temporary, just for the immediate step.
That's really useful. How does an agent actually update this state in ADK code?
There are a couple of ways. The simplest way is often using the output key parameter when you configure an Elm agent. If you set output key last greeting, the ADK runner will automatically take the agent's final text response for that turn and save it into the state under the key last greeting. easy for just saving the last reply. But for more complex updates, maybe you need to update multiple keys at once, store non-text data, or use those specific scopes like user. The standard way is to use eventActions.stataDelta. When your code is appending an event to the session, usually using session_service.appendEvent, you manually construct a dictionary containing the state changes you want to make. This dictionary is your stataDelta. You include the stataDelta within the event actions part of the event object you're appending. This ensures the state change is properly recorded as part of the session history.
Could you give a quick code example, maybe for a tool updating state?
Sure. Imagine a tool function like Lurzer login. Inside that tool, it might get access to something called tool context, which allows it to specify state changes. It could build a stataDelta dictionary like this. Python.stataDelta, user.login count, current count +1, hashtag update user scope count. Task status, login complete, hashtag update session scope status, user.lastlogins.timestamp, hashtag store user scope timestamp, temp.validation needed, false, hashtag set a temporary flag for this turn. The tool would then return this stataDelta as part of its result, and the ADK framework would apply these changes to the session state. This encapsulates state changes neatly within the tool's logic.
And you mentioned something to avoid.
Yes, a crucial point. You should strongly avoid directly modifying the session.state dictionary after you've retrieved a session object. For example, session_service.getSession. Don't just do session.stateMyKey equals new value. This bypasses the proper event processing mechanism. It risks data loss, can cause concurrency issues if multiple things are trying to update state, and it fails to update important metadata associated with state changes. Session.state should primarily be used for reading existing data to inform the agent's logic. Updates should go through the stataDelta mechanism when appending events.
Okay, connecting that state concept back to the crisis agent.
Right. So within a single chat, your agent might set state task status, a kill safety plan drafting, to track the current activity. That's session specific. But if a survivor says they prefer to communicate via text, the agent could trigger an update to state user.prefirstText. True. Because of the user prefix, that preference would be remembered the next time this survivor interacts with the agent, even in a completely new session days later. A tool like Log Survivor Interaction Start could securely update both a session-specific task status and a user scope user.last_interactions using that stataDelta approach.
Perfect. So session is the chat, state is the scratchpad for the chat with some user-level persistence. What about the truly long-term searchable knowledge?
That's where memory and the memory service come in. While session and state handle the conversational flow and temporary data, memory service is designed for managing that persistent, searchable, long-term knowledge base we talked about earlier. ADK defines a standard interface, base memory service, for this. It has core functions like add session to memory, which would typically extract relevant content from a completed session and store it in the long-term memory. And crucially, search memory, which allows an agent to query this long-term knowledge base and receive relevant data back.
And what are the actual implementations for this memory service?
Similar to session service, there's an in-memory memory service for testing again. Data is not preserved. For production environments, especially when you need semantic search capabilities, the key implementation is Vertex LayerAC memory service. This requires pip install Google AC for TextEye. This service leverages Google Cloud's Retrieval Augmented Generation, RAG, capabilities. RA is that powerful pattern where the agent first retrieves relevant information from a knowledge source, long-term memory, and then uses an LLM to generate a response that incorporates that retrieved information. The Vertex LayerAC memory service provides scalable, persistent storage and enables that semantic search. You can configure things like which RAG corpus, your knowledge base to use, how many results to retrieve, similarity topic, and the relevance threshold, vector distance threshold.
So this is where our crisis agent would store things like anonymized best practices or answers to common questions.
Exactly. This is the place for that kind of durable, searchable knowledge. You could store anonymized summaries of successful intervention strategies, frequently asked questions with carefully vetted answers, or maybe generalized descriptions of common crisis scenarios and effective responses. Then, when faced with a new situation, the agent can use search memory, powered by Vertex LayerAC memory service, to perform a semantic search over this knowledge base. It can retrieve best practices or relevant information from similar past situations, all anonymized, of course, ensuring it provides consistent, high-quality responses based on accumulated knowledge and potentially reducing the workload on human experts for common queries.
Okay, the ADK structure makes sense, session, state, memory. But beyond Google's ADK, many developers in the Python AI space are very familiar with LangChain and maybe LangGraph. How do these popular frameworks approach memory management? Is it similar?
Yeah, LangChain and LangGraph definitely consider memory a critical component, It's absolutely central to creating intelligent and natural conversational applications in their ecosystem, too. For them, memory is how an AI agent remembers context, learns from feedback, adapts to user preferences. The stored history enriches the current prompts, making the conversation flow better, and new exchanges get recorded for future use. The core ideas are very similar.
How do they handle short-term versus long-term?
So, short-term memory in LangChain is typically thread-scoped. It tracks the ongoing conversation within a single session or chain execution. In LangGraph, this conversational state, including the short-term memory, is managed as part of the agent's overall state and can be persisted using something called a checkpointer. Long-term memory is for storing user-specific or application-level data that needs to persist across sessions or be shared between different conversational threads. LangChain often talks about saving this in custom namespaces so you can recall it when needed.
Does LangChain offer specific tools or classes for managing conversation history?
Yes, it does. For direct manual control, there's the chat message history class. You can explicitly add user messages, history.adducer_message, and then access the list of messages, history.messages. Useful if you're managing history outside of a formal LangChain chain. More commonly, though, you'd use one of their memory classes that integrates directly into chains. The most basic and widely used one is conversation buffer memory. This just holds a buffer, essentially a list, of the conversation turns. You configure it with a memory key, which is the variable name in your prompt where the history will be injected, often just history. A key parameter is return messages. If it's false, the default, it formats the history as a single string, which older LLMs might need. But if you set return messages true, which is generally recommended, especially for chat models, it provides the history as a list of distinct message objects, human AI system. This preserves the conversational structure much better.
So that conversation buffer memory with return messages, true, would be key for our crisis agent to keep a fluid, empathetic conversation going within a single session, making sure it doesn't lose track of previous statements or emotional cues from the survivor.
Exactly. That setup helps maintain the nuanced context needed for chat models to perform well in ongoing dialogues. It ensures the LLM gets the history in a structured format it understands well, allowing it to respond more coherently and empathetically within that single session.
You also mentioned LangChain having analogs to human memory types for long-term storage. Can you elaborate on that?
Yeah, they often frame long-term memory in these terms, which can be helpful conceptually. Semantic memory, this is about remembering facts, specific concepts, user preferences, domain knowledge. For an agent, this might be stored as a user profile, maybe JSON data, or within a collection of documents, like in a vector store. It's used to ground the agent's responses and enable personalization. For your crisis agent, this is where you'd store facts about regional support networks, specific legal aid contact details, or common safety planning steps that need to be quickly retrieved. Episodic memory. This is remembering experiences or past events. For AI agents, this often translates to remembering how to accomplish a specific task successfully. A common technique here is using few-shot examples, providing the agent with examples of successful past interactions or task completions to guide its current actions. In the crisis context, remembering successful intervention sequences or sequences of actions for common scenarios could guide the agent's problem-solving approach. Procedural memory. This is remembering rules or how to perform tasks. It's essentially the agent's core instructions, its ingrained behaviors, often contained within its system prompt. Interestingly, this can be modified through a process sometimes called reflection, where an agent analyzes its own interactions and refines its own instructions, its system prompt, based on what worked or didn't work.
Wow, so an agent could actually reflect on a difficult conversation where maybe its initial instructions for empathy weren't quite right, and then update its own system prompt to be more nuanced next time.
Precisely. That's the idea behind reflection as a form of procedural memory adaptation. It's a powerful concept for enabling agents to learn and improve their core behaviors over time based on experience, directly enhancing future interactions.
How does LangGraph specifically store these long-term memories?
LangGraph provides a base store interface and implementations, like in-memory store for testing or integrations with external databases for storing long-term memories. These are typically stored as JSON documents, organized under custom namespaces like user profiles or intervention strategies, and identified by distinct keys, like a user ID or a scenario ID. These stores allow you to put data, get data by key, and often search data, potentially using filters or even vector similarity search if the store supports it, requiring an embedding function. So using a LangGraph store, Your crisis agent could save detailed, anonymized outcomes of various support strategies, semantic memory, or perhaps effective prompt sequences used for de-escalation in specific scenarios, episodic memory. These memories, organized by user ID or application context, can then be searched and applied to inform future interactions, making the agent more effective over time. And just to round this off, for those looking for a fully managed, perhaps easier to integrate solution for long-term memory, especially within the Google Cloud ecosystem, there's the Vertex Memory Bank.
Right, you mentioned that briefly with ADK. Tell us a bit more about it. How does it work?
Sure. The Vertex Memory Bank is a managed service, part of the broader Vertex AI agent engine. It uses Gemini models behind the scenes to asynchronously analyze conversation histories that you feed into it. It automatically extracts key facts, details, and user preferences from those conversations. It stores this information persistently, organizing it by a defined scope, typically a user ID. What's really neat is that it intelligently updates itself. As new conversations happen, it consolidates the new data with existing memories, potentially resolving contradictions or refining its understanding of a user's preferences over time. Then, when you start a new session for a user, you can query the memory bank to retrieve the relevant memories for that user. You can either get a full recall or use semantic similarity search using embeddings to find the most pertinent facts for the current context. It integrates seamlessly with Google ADK via the Vertex AI Memory Bank service, but it's also accessible via direct API calls, meaning you could potentially integrate it with other agent frameworks like LangGraph or Crew AI if you wanted to.
So for the crisis response agent, this could be quite powerful.
Immensely powerful. Imagine your crisis response agent automatically feeding anonymized interaction summaries into Memory Bank. Memory Bank would then extract and consolidate key facts over time, details about specific recurring concerns a survivor mentions, known triggers, support preferences they've expressed, steps taken in their safety plan. When that survivor interacts again, the agent queries Memory Bank and instantly gets the synthesized long-term context. This allows it to provide incredibly personalized, informed, and continuous support across multiple engagements. It builds trust and effectiveness in a way that's really crucial for survivors navigating complex, ongoing situations. It's like giving the agent a continuously updated, intelligent briefing document before each interaction.
Okay, fantastic. So our agents can interact with the world using MCP, and they can remember past conversations and knowledge using robust memory management, whether ADK, LangChain, or Memory Bank. But to be truly proactive, truly useful, especially in that high-stakes crisis response environment, they need more than just tools and memory. They need a clear sense of direction, right? They need to know what they're actually trying to achieve.
Exactly. You've arrived at the next key pattern: goal setting and monitoring. This is all about giving agents specific objectives to work towards, and, just as importantly, equipping them with the means to track their progress and figure out if they've actually met those objectives. Without this, agents remain largely reactive. They can answer questions, maybe use a tool when asked, but they can't really orchestrate complex multi-step solutions or proactively drive towards a desired outcome.
It sounds a bit like planning a trip, doesn't it? You define your destination. That's the goal state. You know where you're starting from the initial state. Then you figure out the steps to get there, book tickets, pack, travel.
That's a perfect analogy. In AI agents, planning involves taking a high-level objective provided by the user, or maybe predefined, and autonomously, or perhaps semi-autonomously, generating a sequence of intermediate steps or sub-goals needed to reach it. Once a plan is formed, the agent executes the steps, often using other patterns like tool use, MCP, and memory. The planning mechanisms themselves can range from sophisticated search algorithms, logical reasoning systems, or, very commonly now, leveraging the LLM itself to generate plausible and effective plans based on the goal and the available tools. This ability to set goals and plan enables agents to tackle problems that aren't just simple single-step queries. They can handle multifaceted requests, they can adapt to changing circumstances by replanning if a step fails, and they can orchestrate complex workflows involving multiple tools and information sources. It fundamentally transforms a simple reactive system into one that can proactively work towards achieving a defined objective.
That makes perfect sense. And for our listeners' missions supporting domestic violence crisis response, this concept of goal setting and monitoring feels absolutely fundamental, doesn't it?
Oh, completely fundamental. An agent in this context needs to go beyond just answering questions. It has to be actively working toward a positive, safe outcome for the survivor. For instance, an agent could have a very clear, measurable objective like successfully connect survivor to verified local legal aid resources within the next 15 minutes. Or maybe co-create a basic documented safety plan with the survivor.
Can you walk through how that might look in some practical use cases, adapting from the source material?
Sure, let's adapt some general examples to the crisis response context. Customer support automation, adapted. Imagine the agent's primary goal is defined as safely de-escalate the immediate crisis situation and provide relevant, verified support options. To achieve this goal, the agent needs to monitor the conversation. It would track sentiment shifts using maybe an internal LLM call. It would check its knowledge base, long-term memory, for appropriate de-escalation techniques or responses. It would use tools, MCP, to find local verified resources like shelters or counseling services. Success is monitored by things like Rebeni, confirming the survivor received the information, observing textual cues indicating de-escalation, again, maybe via sentiment analysis, or tracking if a successful handoff to a human expert occurred via a specific tool call. If the issue isn't resolved, or worse, if it escalates, monitoring detects this, the agent's programming must trigger specific protocols, maybe immediately connecting to a human, maybe locking down the chat, depending on safety guidelines. Personalized learning systems, adapted. Let's say a survivor needs to understand their rights regarding a specific type of protection order. The agent's goal might be: ensure survivor understands the key aspects of protection order X. To monitor progress towards this goal, the agent monitors the survivor's questions and responses. It adapts its explanations based on their apparent understanding. It tracks comprehension, perhaps by asking clarifying questions. Does that part of the filing process make sense, or would you like me to explain it differently? If the monitoring indicates the survivor is struggling, the agent adjusts its approach, maybe using simpler language or offering a different resource, until its internal check indicates the goal, comprehension, is likely met. Project management assistance, adapted. Think about the intake process. An agent could be tasked with the goal: complete the survivor's initial intake form data collection by the end of the session. It monitors which fields are filled, prompts politely for missing information, maybe validates inputs using tools. It flags delays. If the monitoring shows the intake goal is at risk, maybe the session is nearing its time limit or the survivor seems hesitant, the agent could suggest corrective actions, like offering to save progress and continue later, or asking if they'd prefer to switch to a human worker.
This sounds incredibly sophisticated. It's like the agent needs to be its own internal project manager, constantly checking its work against a checklist or a set of quality criteria defined by the goal. Can you give us a more hands-on example, maybe conceptually in code, of how this iterative process of working towards a goal and self-monitoring might look?
Precisely. It often involves this kind of iterative loop: act, evaluate, refine. We can illustrate this with a conceptual Python code example. Let's imagine, drawing inspiration from the book, an autonomous AI agent designed to generate and then iteratively refine Python code itself. Its goal is to produce code for a specified use case that meets certain quality benchmarks defined by the user.
Okay, an agent that writes and refines code based on goals, how would that work?
Conceptually, the objective is to build an AI agent that writes code for a use case, like find the binary gap of an integer, based on specified goals, like code must be simple, must be tested, must handle edge cases, must be functionally correct. It would operate in an iterative cycle: create code, self-evaluate against the goals, improve the code based on the evaluation. This loop would run for a set number of max iterations, say 5, to prevent it from running forever. Crucially, the agent's success monitoring relies on its own AI-driven judgment. After each iteration, it would essentially ask another LLM call: based on the feedback received, does the current code now meet all the initial goals? Answer only true or false.
So how would the code structure look, roughly?
You'd need a few key functions: generate prompt. This would construct the prompt for the code writing LLM. It would include the use case, the list of goals, the previous code, if it's refining, and any feedback from the last evaluation. Get code feedback. This function would likely use another LLM call, acting as a simulated Python code reviewer. It would take the generated code and the goals and critique it, providing textual feedback on what needs improvement: clarity, simplicity, correctness, edge cases, test coverage, etc. Goals met. This is the critical monitoring function. It takes the feedback text from the reviewer LLM and the original goals and uses a separate simple LLM call configured to just output true or false to determine if the feedback indicates all goals have now been satisfied. Utility functions. You'd probably have helpers for cleaning up the LLM's code output, clean code block, maybe adding comments, add comment header, formatting file names, snake case, and saving the final code, save code over file. The run code agent function would be the main loop. It parses the input use case and goals. It enters a for loop up to max iterations. Inside the loop, it generates code, gets feedback, then calls goals met. If goals met returns true, it breaks the loop. If false, it uses the current code and feedback to go into the next iteration for refinement. Finally, it adds a header and saves the best version achieved.
You can run this from the command line, right?
Right.
Give it a use case and the goals.
Exactly. You might run it like Python codeagent.py use case. Write code to find binary gap of a given positive integer goals. Code simple to understand, functionally correct, handles comprehensive edge cases, takes positive integer input only, prints the results with few examples. The agent would then iterate, trying to satisfy all those specific requirements.
This iterative refinement and self-checking against goals is fascinating. But you mentioned using an LLM to critique code written by another LLM, or maybe even the same LLM. That sounds potentially problematic. Could the LLM just convince itself it did a good job, or completely misunderstand a goal?
You've hit the nail on the head. That's why it's crucial to understand the caveats and considerations here. This code agent example is an exemplary illustration of the goal setting and monitoring pattern, but it's not production-ready code, especially for critical applications. You're absolutely right. An LLM might not fully grasp the intended meaning or nuance of a goal like simple to understand. It might hallucinate features or correctness. It could definitely incorrectly assess its own performance as successful, especially if the same LLM instance is both writing and judging the code. It lacks true objective oversight. LLMs don't magically produce flawless code. You still need to run, test, and validate the output yourself. The basic true-false monitoring in this simple example is quite brittle. It could easily lead to an infinite loop if the goals are contradictory or too difficult, which is why having that max iteration safety net is essential.
So if this single-agent approach has these weaknesses, how do we build something more robust, more reliable, especially when thinking about the high stakes of domestic violence crisis response, where accuracy and safety are absolutely paramount?
For real-world applications, particularly sensitive ones, a much more robust approach involves separating these concerns using a multi-agent crew. Instead of one agent trying to do everything, write, review, monitor, you assign specific roles to a team of specialized agents. You might have a peer programmer agent, responsible for writing the initial code, a code reviewer agent, a separate agent with a prompt specifically designed to critically evaluate code against standards and goals, a documenter agent, a test writer agent, which directly addresses the need for testing, maybe even a prompt refiner agent that helps improve the initial request.
So the code reviewer is a completely separate entity with its own perspective and prompt, not the same agent just switching hats.
Exactly. That separation significantly improves the objectivity of the evaluation. The reviewer agent's sole purpose is to critique based on the goals, reducing the risk of the programmer agent deceiving itself or overlooking flaws. This structure also naturally leads to better software development practices, for instance. Having a dedicated test writer agent ensures that the goal of having tested code is explicitly addressed by generating actual unit tests.
Okay, let's map this multi-agent crew concept directly onto the crisis response scenario. How does separating concerns increase trustworthiness and effectiveness there? Accuracy and safety are just non-negotiable.
This multi-agent approach is perfectly suited for increasing trustworthiness in that context. You could structure your AI system like this: a crisis assessment agent. Its sole focus is gathering initial information from the survivor, assessing immediate safety risks, using maybe a structured protocol. Its goal is clear: gather key initial data safely, a resource navigator agent. This agent's goal is to find and verify appropriate help options, shelters, legal aid, counseling, based on the assessment. It would use MCP tools to query databases and APIs. Its monitoring checks if verified relevant resources were successfully identified and presented. A safety plan reviewer agent. If the interaction involves safety planning, this specialized agent could review the co-created plan, perhaps drafted by the assessment agent or a human, against established best practices and safety guidelines stored in its knowledge base. Its goal is validation, and crucially, perhaps an empathy monitor agent. This agent runs in the background. Its goal is to continuously analyze the conversational tone and content of the primary agent's messages. It monitors for language that might be perceived as judgmental, insensitive, triggering, or unhelpful, flagging potential issues for review, or even triggering an immediate human takeover if necessary.
Wow. That's separation of duties, especially having dedicated reviewer and monitor agents. Sounds like it would dramatically increase the safety and reliability compared to one agent trying to juggle everything.
It absolutely does. This separation of concerns significantly boosts the trustworthiness, robustness, safety, and overall effectiveness of the AI system. It allows for specialized tuning of each agent's prompt and behavior and provides layers of validation and oversight. This is absolutely critical when you're building AI to support survivors in potentially life-threatening situations. It's not just about making the AI work, it's about making it work safely and responsibly.
Okay, we've covered a lot. Agents can interact with the world, MCP. They can remember memory, and they can work towards specific objectives, even monitoring their own progress, goal setting and monitoring, ideally using specialized multi-agent crews for reliability. What's the ultimate next step then? How do these agents get genuinely smarter over time? How do they adapt to new challenges, become more effective, especially in a field as incredibly nuanced and dynamic as crisis response, where situations are rarely textbook?
That brings us to the final and perhaps most exciting pattern, learning and adaptation. This is really pivotal for truly enhancing AI capabilities. It enables agents to evolve beyond their initial programming, to improve autonomously based on their experiences and interactions with the environment. This ability to learn and adapt is absolutely vital for managing novel situations, optimizing performance over time, and reducing the need for constant manual intervention and reprogramming by developers.
So how do agents actually learn and adapt? What does that look like under the hood?
Well, at its core, learning and adaptation for an agent means changing its internal state, its thinking processes, its actions, its knowledge base based on new experiences and incoming data. This allows them to become more effective or efficient over time. There are several key types of learning relevant to agents. Reinforcement learning, RL. This is where agents learn through trial and error. They try actions, receive positive feedback, rewards for good outcomes, and negative feedback, penalties for bad ones. Over time, they learn policies or strategies that maximize rewards. This is classic for controlling robots or playing complex games, but the principles apply to optimizing agent behavior too. Supervised learning. Agents learn from labeled examples. They're shown inputs and the corresponding desired outputs, learning to map between them. This is common for tasks like classification or decision-making based on recognized patterns. Unsupervised learning. Here, agents learn from unlabeled data, discovering hidden structures, connections, or patterns on their own. This can help agents organize information, gain insights, or build internal mental maps of a domain. Few-shot, zero-shot learning, especially for LLM-based agents. Modern LLMs are remarkably good at this. They can often adapt to new tasks or instructions with just a few examples, few-shot, or sometimes even just based on a clear description of the task, zero-shot, without needing extensive retraining. Online learning. This is crucial for dynamic environments. Agents continuously update their knowledge or models as new data streams in, allowing them to react and adapt in real time. Memory-based learning. Agents explicitly use their stored memories, both short-term and long-term, to inform current decisions. Recalling similar past situations helps them adjust their actions, enhancing context awareness and decision-making. Adaptation, then, is the visible result of this learning. It's the change you actually see in the agent's behavior, its knowledge, or its strategies. This ability to adapt is what makes agents truly useful in unpredictable, changing, or completely new environments.
For LLM-based agents specifically, are there particular algorithms used to help them learn from feedback, especially human feedback, to make them safer or better aligned with our goals? You hear terms like PPO or DPO thrown around.
Yes, those are two important ones, especially in the context of aligning LLMs with human preferences, which is critical for safety and usefulness. Proximal policy optimization, PPO, is a type of reinforcement learning algorithm. It's often used to train agents, including fine-tuning LLMs. Its core idea is to make small, careful updates to the agent's policy, its way of making decisions or generating text. It uses a clever mathematical trick, a clipped objective function that acts like a safety brake. It prevents the updates from changing the policy too drastically in one go, which helps ensure the learning process is stable and doesn't suddenly make the agent behave erratically. Direct preference optimization, DPO, is a more recent method, specifically designed to be a simpler and often more effective way to align LLMs directly with human preferences, compared to the older RLHF reinforcement learning from human feedback methods that typically used PPO.
How does DPO differ from the older PPO-based approach for alignment?
Okay, so the traditional RLHF approach, often using PPO, was usually a two-step process. First, you'd collect human preference data. Humans saying, I prefer response A over response B. You'd use this data to train a separate reward model. This model learned to predict which response a human would prefer. Second, you'd use this trained reward model as a kind of judge within a reinforcement learning loop, using PPO, to fine-tune the main LLM. The LLM would get rewards from the reward model for generating responses that the reward model predicted humans would like. This process can be quite complex, involve training multiple models, and sometimes be unstable.
And DPO simplifies this.
Exactly. DPO cleverly skips the need to train a separate reward model entirely. Instead, it uses the human preference data, the A is better than B pairs, directly to update the policy of the main LLM. The math behind it essentially teaches the LLM. Increase the probability of generating responses like the preferred one, A, and decrease the probability of generating responses like the disfavored one, B. It optimizes the LLM's policy directly based on the preferences, making the alignment process simpler, often more stable and more efficient because you're only training one model.
So for our crisis response agent, DPO would be a way to directly fine-tune the base LLM using feedback from human crisis experts. They could provide examples of good versus bad or preferred versus disfavored responses in specific sensitive scenarios.
Precisely. That's a perfect application. You could collect preference data from experienced crisis counselors. They could rate or compare different ways the agent might respond in tricky situations. Using DPO, you could then directly fine-tune your agent's underlying LLM to make it more likely to generate responses that align with those experts' judgments, making it more empathetic, more accurate, safer, and more aligned with best practices in crisis intervention. It's a powerful technique for embedding expert human values directly into the model's behavior, which is critical for building trust and ensuring positive impact in such a sensitive domain.
It really sounds like a continuous cycle of improvement then. How do these adaptive agents actually demonstrate better performance over time, especially in variable environments like crisis response where every situation is unique?
They demonstrate it through those iterative updates driven by experiential data. As new patterns are identified, perhaps flagged by human moderators, these examples can be used to refine the agent's internal detection models, maybe using supervised learning or few-shot learning, enhancing the system's security, and better protecting vulnerable individuals from online risks. Recommendation agents adapted. When suggesting resources, an agent can learn what's most helpful. By employing user preference learning algorithms, maybe based on implicit feedback like click-through rates on suggested links or explicit feedback like, was this resource helpful? The agent can improve the precision of its content selection. It learns to provide highly individualized and contextually relevant recommendations suggesting the specific type of support resource or the exact local legal aid contact that has proven most effective in similar past situations for other users, again, always anonymized. Knowledge-based learning agents, RG. Agents using R can make their knowledge base dynamic. They don't just retrieve information, they can potentially add to it. By storing summaries of successful strategies, anonymized case notes about challenges encountered, or newly discovered resources, the agent's knowledge base grows over time. When making decisions, it can reference this richer, experience-based data, enabling it to adapt to new situations more effectively by applying previously successful patterns or actively avoiding known pitfalls learned from past interactions.
This goes way beyond just tweaking prompts, doesn't it? It sounds like the agent itself is fundamentally changing, improving its own logic or knowledge based on what it experiences. Are there real-world examples where agents literally modify their own code to get better? That still sounds a bit like science fiction.
It does sound like science fiction, but yes, this is where things get really interesting and push the boundaries. The self-improving coding agent, or SICA, developed by researchers Maxime Robins, Lawrence Aitchison, and Martin Summer, is a truly groundbreaking example of this kind of agent-based learning.
An agent that modifies its own source code. How does that even work?
It's pretty wild. The core concept of SICA is exactly that. It's an agent that acts as both the modifier and the entity being modified. It iteratively refines its own code base to improve its performance on a set of benchmark coding challenges. It follows an iterative self-improvement cycle. SICA looks at an archive of its previous versions and how well they performed on tests. It picks the version with the highest score, then it analyzes the whole archive to identify potential ways it could improve its code. It directly alters its own source code files to implement those improvements. Then it tests the newly modified version, records the results in the archive, and repeats the whole process, aiming to climb the performance ladder.
That's incredible. So, translating that concept, imagine a crisis response agent that, based on structured feedback from human experts about its past interactions, could potentially adapt its own internal logic or communication scripts, maybe refine how it detects subtle cues of distress, or improve the parameters it uses to search for resources.
Exactly. That's the paradigm shift. It moves beyond humans debugging and reprogramming the agent towards the agent having some capacity for autonomous improvement based on performance feedback. It could learn to handle nuances better or optimize its internal processes based on what demonstrably works best in the real world, as judged by expert feedback.
What kind of specific self-improvements did Seca manage to discover on its own?
It came up with some remarkably sophisticated improvements. Code editing. It started with basic file overwriting, but evolved itself to create a smart editor. Then it developed a diff-enhanced smart editor using code differences, diffs, for more targeted modifications and even pattern-based editing. It even implemented optimizations like minimal diff output and used abstract syntax tree, AST, parsing understanding the code's structure for context-sensitive diff minimization. It basically taught itself smarter ways to edit code, navigation. To find where to make changes in the code, it independently created an AST symbol locator, using the code's structural map to find function or variable definitions accurately. Later, it combined this with faster search methods to create a hybrid symbol locator. It was inventing its own developer tools.
That's amazing. Did Seca's architecture have any special features to manage this self-modification process safely? You mentioned multi-agent crews earlier.
Yes, Seca's architecture had some interesting details relevant to managing complexity and safety. It had a foundational toolkit for basic operations, file I/O, running commands, etc. It used specialized subagents. Seca wasn't monolithic. It included specific subagents for coding, problem-solving, and reasoning. These help decompose complex improvement tasks and manage the LLM's context length during long-running improvement cycles. It featured an asynchronous overseer, essentially, another LLM running concurrently. This overseer monitored Seca's behavior, looking for problems like infinite loops, stagnation, or inefficiencies. It received detailed reports, like a call graph showing function calls, logs of messages, tool actions. If it detected a problem, it could intervene by sending notifications to Seca or even halting its execution. It used a structured LLM context window, carefully organizing information like the system prompt, goals, tool docs, the core prompt, problem files, and assistant messages, reasoning, tool calls, overseer messages to maintain clarity. Crucially for safety, given its ability to execute shell commands, the research strongly emphasized running Seca within a Docker container, isolating it from the host machine. It also had robust observability features, like an interactive web page visualizing events and the agent's call graph, helping developers understand what it was doing.
That idea of specialized subagents, and especially an overseer LLM, seems incredibly relevant for sensitive applications like crisis response.
Absolutely. It directly maps to the multi-agent crew concept we discussed for increasing robustness and safety. In a crisis context, your primary support agent could rely on a resource search subagent and a legal information subagent. But the critical addition is that ethical overseer agent. Its sole purpose is to monitor the primary agent's interactions against ethical guidelines, safety protocols, and empathy standards, intervening or alerting a human if boundaries are crossed. This multi-agent structure with dedicated oversight significantly enhances safety, accountability, and trustworthiness in such a high-stakes environment. And beyond Seca's self-improving code, Google has also developed AI agents that demonstrate another facet of learning and adaptation, autonomously discovering and optimizing algorithms themselves.
Like AlphaFold for algorithms.
Kind of. AlphaVolve is an AI agent developed by Google specifically for this. It uses a combination of LLMs, like Gemini Flash for generating ideas, Gemini Pro for analyzing and refining them, automated evaluation systems, and an evolutionary algorithm framework. The impact has been pretty significant. It's been deployed within Google's infrastructure, finding optimizations that led to a measurable reduction, 0.7%, in global compute resource usage for data center scheduling. It's optimized low-level Verilog code for TPUs. It's accelerated AI performance, like finding a 23% speed improvement in a core Gemini kernel. And on the research side, it's discovered genuinely new algorithms for things like matrix multiplication and rediscovered or improved state-of-the-art solutions for dozens of open mathematical problems. There's also OpenEvolve, which is an open-source evolutionary coding agent framework. It also leverages LLMs to iteratively optimize code. It orchestrates a pipeline of LLM-driven code generation, evaluation, and selection to continuously enhance programs. It supports multiple languages, can evolve entire files, and has features like multi-objective optimization and distributed evaluation. You can actually run it yourself with a simple Python script, pointing it at an initial program and an evaluation file, and letting it iterate to find better versions.
These examples, AlphaVolve and OpenVolve, really drive home the potential of this iterative, autonomous improvement, don't they?
They absolutely do. It's a powerful illustration. While your initial crisis response agent might be carefully and effectively designed based on current best practices, imagine it having the capability to evolve over time. To autonomously optimize its strategies for offering support based on anonymized outcome data from thousands of interactions, or discovering more efficient ways to access and synthesize crucial information for survivors in real time. This is how AI moves beyond being just a static tool. It's how it can genuinely augment human capabilities in a complex field like domestic violence crisis response, becoming ever more effective, precise, and responsive without requiring constant manual reprogramming for every little improvement. It becomes a partner that learns and adapts alongside the humans it supports.
Wow. Okay, we have covered a tremendous amount of ground today. From agents just making their first connections to the outside world, all the way to agents that can literally improve their own code. Let's try to quickly recap some of the absolute key takeaways for our listener who's aiming to build these more advanced AI solutions.
Definitely. It's been a journey. So we started with the Model Context Protocol, MCP. Remember that universal adapter? It's the open standard allowing LLMs to consistently discover and interact with external resources, databases, APIs, custom tools. For your crisis agent, this is how it securely accesses real-time shelter data or sends those critical secure notifications. The key insight: MCP standardizes how your agent plugs into the world.
Right. Then we dug into memory management, that crucial dual system. Short-term memory in the context window, managed by ADK's session and state or LangChain's buffer memory for immediate coherence, and long-term persistent memory, using ADK's memory service with RA, Vertex Memory Bank, or LangChain LangGraph stores, often with vector databases, for retaining knowledge, preferences, and history across sessions. Remembering a survivor's specific needs or past disclosures is absolutely paramount for building trust and providing continuous personalized care.
Exactly. Next up was goal setting and monitoring. This gives agents purpose and direction. It's about defining clear objectives like connect survivor to legal aid and enabling the agent to plan steps, execute actions using MCP tools in memory, and critically monitor its own progress towards that goal. Your agent doesn't just passively chat, it actively works towards achieving a positive outcome and knows whether it succeeded or needs to adjust its plan. Using multi-agent crews here adds that vital layer of reliability and safety.
And finally, we explored the really incredible power of learning and adaptation. This enables agents to evolve, to improve their strategies, their knowledge, even their own underlying logic or code, autonomously based on experience and feedback. Using techniques like RL, DPO, or architectures like Sika or AlphaVolve. This is where AI truly transitions from being just a sophisticated tool to becoming a constantly improving, adaptive, intelligent partner.
And for you, our listener, working to support these vital domestic violence crisis response organizations. These agentic design patterns, they aren't just abstract computer science concepts. They are the practical building blocks. They let you create AI solutions that are so much more than just chatbots. They empower your AI to securely access that local shelter database now, to remember the nuances of a survivor's evolving safety plan over weeks or months, to proactively check if a referred resource was actually helpful, and crucially, to continuously get better, safer, and more empathetic at providing that vital support, learning from every interaction in an anonymized, ethical way, of course. You're not just building chatbots anymore. You're building agents that can genuinely augment human compassion with incredible precision, persistence, and efficiency.
So, as you step forward, the Python beginner with 6 months under your belt, already proficient with prompt engineering, now ready to build these truly advanced AI solutions. Maybe consider this question. What complex multi-step problem within domestic violence crisis response, something currently requiring intense, time-consuming human expert intervention, could be potentially augmented, maybe partially, maybe even significantly, by an AI agent equipped with these patterns? An agent that can intelligently interact with real-world systems, remember critical details across time, set clear, measurable goals for assisting a survivor, and perhaps most importantly, learn and adapt from every single interaction. How can you start thinking about embedding these cycles of goal-driven action, monitoring, and even self-improvement into the AI solutions you build? How can you transform them from static tools into truly adaptive, compassionate, and profoundly effective partners in the critical life-saving work of crisis response?